Okay, everybody, welcome to Calculus 2. Today we're going to be covering solids of revolution. So there are some properties you need to know about solids of revolution before we get started, so we're going to get into that first. So what is a solid of revolution? Well, if we let S be a solid that lies between x equals a and x equals b, if the cross-sectional area of S in the plane p of x through x and perpendicular to the x-axis is the function a of x, where a is a continuous function, then the volume of S can be represented by this formula here, which basically says the volume is equal to the limit as h approaches 0 of the summation starting at I equals 1 and going to n of a of x sub I raised to n times delta x. And that might look daunting or challenging at first, but that's really just the Riemann sum from Calculus 1. It's the width times the height of infinitely small rectangles on a graph. And that can be simplified down to the integral of a of x dx from the interval from the lower limit a to the upper limit b. And so it might be a little bit confusing to kind of think about how you can find a volume of a solid if you place it on a graph. So what I've drawn here is I've gone and tried to draw a visual aid. So basically imagine if you have a 3D cube in the x, y, and z planes. If you wanted to find the volume of that cube, which is the length and the width and the height, you could just slice it up into infinitely small slices of that cube and make squares instead of cube, because they would be slices, like very thin slices. They would be dx in width. So you have these infinitesimally small in width. They're infinitesimally small in width, but they're the same height and the length. And if you add up all those areas, you could just take up the areas of all those slices, and if you add them all up, you would get the volume of that cube. So it's the same thing with a solid of revolution. Essentially what you're doing is taking the integral, so you're dividing it up into very small pieces and then adding up all those areas. So that's why it's a of x, because it's the area. A solid of revolution is obtained by rotating a region about a line, and generally we can calculate the volume of a solid of revolution by using the basic defining formulae. So if you need to take an integral with respect to the y, you use the one on the left here, the integral from a to b of a of x dy. That should be dx actually, not dy. Or if you need to take it with, so this left one is if you need to take it with respect to the x-axis, and this y one is if you need to take it with respect to the y-axis. And it's the same thing, you just change your x's to y's. And there are going to be certain problems where it's easier to integrate with respect to the y-axis or the x-axis. So you'll see when we get to the practice problems. And then if we look over here, we have some more information. We can find the cross-sectional area a of x or a of y in one of the following ways. If the cross-section is a disk, we find the radius of the disk in terms of x or y and use a equals pi times the radius squared. And a disk is basically, in this case, just a solid circle. If the cross-section is a washer, which means it's shaped like a donut, it has a hole in the middle, we find the inner radius, which I've denoted as r sub inner, and the outer radius, which I've denoted as r sub outer, and compute the area of the washer by subtracting the area of the inner disk from the area of the outer disk. So if you look at this washer here, this small line is the radius of the inner circle, or the inner radius, and this longer line is the outer radius. So we're going to subtract the area of the inner disk by the area of the outer disk, and we would just get the area of this black region right here. So now that I've introduced you to the concept, let's get to some practice problems. Okay, so in this next problem, we're asked to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. And the information we're given is that y equals 2 minus 1/2 x, y equals 0, x equals 1, and x equals 2. So these three equations, the y equals 0, x equals 1, and x equals 2, are the curves that this equation is going to be bounded by. So we go ahead and take a look at the graph here. We can see that this is all mapped out by this graph, and these red dotted lines are these three equations right here. So we have y equals 0, x equals 1, and x equals 2. Now all we have to do is plot the points of this graph, and I'm only going to plot them between x equals 1 and x equals 2 because that's the only interval that we care about. So if I start at 1, if I plug in 1 to 2 minus 1/2 x, I'll get 2 minus 1/2, which is 3/2. So if this number line, if this y-axis is going by 1/2, if it's scaled by 1/2, this would be 1/2, this would be 2/2, and this would be 3/2. So this point is going to be right there. And then for x equals 2, if I plug in 2 for x, then I will have 2 minus 1, which is 1. So it would be like that, because 2/2 is the same thing as 1, if this is going by halves. So, and then I connect the line right there. And we can see now that the region we want to rotate is this one right here. This region is between all three, or technically all four of the curves if you're counting this one as well, and we are. So now it's very tricky definitely to rotate a shape like this around around y equals 0, but if we were to do it, it would look something like this. So it'd start to come around like this, and it would go around. Here's it going around the x-axis, and then it circles back like that. And we do the same thing like that with x equals 2. And it goes around and around like that. And you can see, even though I didn't draw perfectly, you can see that if you took a cross-section of this, or you should be able to see that if you took a cross-section of this, it would be a disc shaped. So we're going to use the disc method to find the volume of this curve. Now remember, to find the volume of the curve, it's the integral from a to b of the area of the solid. And I'm going to take it with respect to the x-axis just because it would be easier that way. If you look at it, it would just be easier to do it with respect to the x-axis, so that's what I'm going to do. So because we're using the disc method, I guess first I should talk about the interval. The interval is going to be from 1 to 2, like this. And because we're using the disc method, the area is going to be pi times the radius squared. And dx. So the radius is going to be 2 minus 1/2 x. Because if you imagine, if you start here and you go this way, it's only the length of 2 minus 1/2 x, if that makes any sense. You can't go you can't go way out here or something like that for your radius. You have to stay within these bounds, and so the radius would be 2 minus 1/2 x. So pi times 2 minus 1/2 x squared dx. And now I'm going to move the pi to the outside because pi is a constant, and we know from our properties of integrals that you can move constants to the outside of the integral. So I'm going to get 1/2. So 2 minus 1/2 x squared is going to be 1/4 x squared minus 2x plus 4. And if you want to know why that is, we can just do it long form right here. 2 minus 1/2 x times 2 minus 1/2 x. So this 2 and 2 multiply to give us our plus 4. Then the 2 and the negative 1/2 x give us negative x, and the negative 1/2 x and the 2 give us negative x, so negative x minus x is negative 2x, and then this negative 1/2 x times negative 1/2 x is positive 1/4 x squared, and we're still going to have our dx there. Now we need to actually evaluate the integral. So I'm going to have pi here, and I'm gonna do a close bracket just to emphasize that pi is going to be multiplied against whatever our final answer is. So when we do the integral of 1/4 x squared, I'm gonna write x cubed, and then this is going to be 12, and this is 1. So you're trying to think of if I took the derivative of this, would I get this back? And I would. I would drop down the 3. 3 divided by 3 over 12 is 1/4, and then 3 minus 1 up here would be 2. So that's how you would do that one. Then this would be x squared, because again, let me write that better. Because again, if we drop down the 2, we get minus 2x, and then this would be 4x, like that. And this is going to be on the interval of 2 to 1. So then I'm going to get pi times 1/12 times 2 cubed minus 2 squared. 2 squared plus 4 times 2. And then I'm going to subtract that by 1/12, and then 1 cubed is just 1, 1 squared is just 1, and 4 times 1 is just 4. So it's going to be 1/12 minus 1 plus 4, like that. And this is like a separate term. Oh, I did not mean to write 2 here. This should be a 1. No, I did mean to write 2 there. Sorry. This is going to be closed off in parentheses. These are separate terms. So I'm going to erase this now, so make sure you have this written down. Okay, so if we bring this back up here and do some simplification, we're going to have pi times 1/12 times 8 minus 4 and then plus 8. And then that's going to be minus 1/12 plus 3. So then this is going to be pi times, we can simplify this, 8 divided by 4 is 2, and then 12 divided by 4 is 3. So 2/3 minus 4 plus 8. And then we're going to have minus 1/12 plus, put a 12 down here, and 3 times 12 is 36. So close parentheses and then close bracket. And then pi times 2/3 plus 4 minus, and then this is going to be 37 over 12. There should not be an open bracket there. minus 37 over 12, like that. And then we're going to get pi times 2/3 plus 2/3 plus 12/3, like this. 12/3 minus 37 over 12. Then we're going to get pi times, so here we're going to add together the 2 and the 12 to get 14/3 minus 37/12. I'm going to erase what's on the bottom here. So then we're going to multiply both the numerator and the denominator of 14/3 by 4 to get it to be a like denominator with this. So this is going to be 12, and then 14 times 4, if I do some just multiplication by hand here, is going to be 56. Let me write that better. 56. So 56 over 12 minus 37 over 12, and 56 over 37 is 19, so we're going to get 19 pi over 12. And that is how you would do that problem. So what this means is that the volume of the solid of revolution, basically this shape right here, has a volume of 19 pi over 12 units. So that's how you do that one. Okay, so in this next question we're asked to do the exact same thing, to find the volume of the solid obtained by rotating the region bounded by the given curves across about the specified line, but this time we're given different information. We're given y equals the square root of x minus 1, y equals 0, and x equals 5. So once again, I'm going to go to the graph here to try to give a visual aid to this. So we've got this graph here, and this red dotted line represents y equals 0, and this red dotted line going vertically represents x equals 5. So if we want to draw the curve out, we have to start at x equals 1, because anything less than 1 we'd get a negative number under the square root. So at x equals 1, y would equal 0, because 1 minus 1 is 0, and the square root of 0 is 0. At x equals 2, 2 minus 1 is 1, the square root of 1 is 1, so y equals 1, or y would equal 1, yeah. And then at 5 right here, everything else would be a decimal. X equals 3 and x equals 4 would be decimals. At x equals 5, 5 minus 1 is 4, and the square root of 4 is 2. So that would be up here. So we have a line that looks like that. And you can see here that even though we don't have a third curve like we did in the last problem, we still have a bound here. We have this shaded region. It can't be anything under here. The curve can't go under here, like between 0 and 1, because once again it would be negative under the square root. So because of that, we know that our bound is this. And when we go to draw a 3D image, it would look, or if we go to draw a 3D image and rotate it around the x-axis, it would look something like this. It would come around like this. It needs to be more curved than that. Come around like this. And then for this one, it would do pretty much the same exact thing. Like that. And then this line would come down here. And you can see now that we have this kind of conical shape like this. And if you took a slice out of this, like for example, this right here, if you took this slice that I'm shading in right now, you'd be able to see that it's just a flat disk. So we know that we're going to be once again using the disk method with this. So to find the volume of a disk, or to find the volume of a solid of revolution using the disk method, it's going to be the integral from a to b of the area with respect to x. So our interval is going to be from 1 to 5. And the reason that it's from 1 to 5 is because the graph only exists from 1 to 5. If it goes beyond 5, it would be beyond this bound, and it wouldn't be able to do that. And if it goes below 1, it would be an imaginary number. So our area function, because we're using the disk method, is going to be pi times the radius squared and dx. So then our radius is going to be square root of x minus 1. So we're going to have pi times the square root of x minus 1 squared dx. So I'm going to move pi to the outside here. So pi times the integral of from 1 to 5 of, and then square root of x minus 1 squared is just x minus 1. So x minus 1 dx. Now when we go to evaluate this integral, I'm once again going to make close brackets. This x is going to become 1/2 x squared, like this, because if we were to drop down this 2, it would become x, and 2 minus 1 is 1, so we'd be left with the x. And then this minus 1 is just going to become minus x on the interval of 1 to 5. So then if we expand this out, we're going to have 1/2 5 squared minus 5, and then that's going to be 1/2 minus 1, because 1 squared is 1, and if you just plug in 1 for x, you're going to get 1. Even though these are separated by a minus sign, I still want to emphasize that pi is going to be multiplied to whatever the final answer of this is. So then that's going to give us pi times 1/2 times 25, and I'm just going to turn this 5 into 10 halves because we're going to have to simplify that eventually. So 10 halves minus, and then 1/2 minus 1 is negative 1/2, like that. And then if we go up here, we're going to have pi times 25 over 10, or 25 over 2 rather, minus 10 over 2. And then this minus and minus and negative is just going to make a plus. So we're just going to be left with plus 1/2, 1/2, like this. So then that's going to give us, if we simplify this, it's going to be 25 minus 10 is 15 over 2. 15 over 2 plus 1/2. Then 15 over 2 plus 1 over 2 is 16 over 2. So we're going to have pi times 16 over 2. And then if we simplify that down, that would just be 8 pi. And that would be my final answer. Okay, so in this next problem we're asked to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. And the information we're given now is that x equals 2 times the square root of y, x equals 0, and y equals 9. So once again we're going to go to the graph, and this is the graph I have set up right now. So you can see that we have the x-axis like this, and the y-axis set up like this, where the red dotted line is this y equals 9, and this x equals 0 would just be the y-axis. So now we can start off by graphing x equals 2 square root of y. And to make it easier for graphing purposes, I'm actually going to solve this in terms of y. So in order to do that, we divide by 2 on both sides to get x equals 2. And that's going to be equal to the square root of y. And then we square both sides. So this becomes x squared over 4. And then this becomes y. So we have y equals x squared over 4. So if we plug in 0, we're going to get 0. If we plug in 1, we're going to get 1/4. So that's going to be like somewhere over here maybe. Then if we, let me make that a circle actually. If we plug in something like 2, 2 squared is 4, and 4 divided by 4 is 1. Then 3 squared is 9, and then that would be like 2 1/4, so somewhere like this. Then 4 squared is 16, divided by 4 is 4. 16 divided by 4 is 4, yep. So like that. And then 5 squared is 25, divided by 4 is going to be 6 1/4, so if this was 4, then this is 5, and this is 6 up here. So 6 1/4 would be like this. And then at 7, it would go beyond y equals 9. So I'm going to draw the parabola like this. And it would basically look, since this equation is, it has symmetry with the y-axis, you can basically just reflect these points here. So it would basically look like this. And now we can see that this would be a washer, and the way we can see that is if we draw it as a 3D object, as if we're rotating it. So if we rotate it, it would look like this. And this is going to go off the page, but whatever. Like that. And then we can even do it with other points, like this one down here. We can do it here. And we can demonstrate that it would be a disc shape. You can see that this is a disc shape, and you can do that with all the points here, and you would find that it's a disc shape. So once again, we're going to use the disc method. The only difference is that now when we find our volume, we're going to do the integral from a to b with respect to y. So it's going to be a of y dy. So because we're using the disc method, our formula for area is just going to be pi times the radius, and our interval is going to be 0 to 9 because we're doing it with respect to the y-axis. So we're looking at the y-axis here, and we're going, it bounds from 0 to 9. So our interval is 0 to 9, and then our area function is going to be pi times the radius squared dy. Now I'm going to move the pi out here, and it's going to be 0 to 9 of the function 2 square root of y squared dy. So then that's going to be pi times, or pi times the integral from 0 to 9 of 4y dy. Now when we evaluate the integral, that's going to be pi times, and then this 4y is going to become y squared, and this number in front is going to be 2, because it's, if we drop down the 2, it would be 4, and then this 2 minus 1 would be 1, so 4y. And that's going to be on the interval of 0 to 9. So then we get pi times 2 times 9 squared. And this is 0, 1, 2 times 0 squared would just be 0, so I'm just going to leave that part out. And so we're going to have pi times 2 times 81. And that is going to give us our final answer of 162 pi. And that would be my final answer for this one.